We've got to engineer things so that at most only one of them is ever active. Okay? Now we do have some additional address lines here. The problem is each of these devices doesn't have any more address lines. But what you tend to find is manufacturers of these devices, they provide you with a special signal, a special pin, which is called chip enable. And it's very, very common. It's usually only one pin, and if the pin is in one state, now it could be high or low, but they'll tell you, the manufacturer, if it's in one state, effectively the whole device goes to sleep and does nothing. And in the other state, the device is awake, and anything you write to it will go into it, and anything you read from it will come out of it. Okay? So what I could now do is I could wire this up like this, but I can now use these other lines connected somehow to these additional address lines here to make sure that at any point in time only one of these is awake. Okay? Now, I've only got two here, so I'm going to have some little bit of combinational logic, but with two things here, there are four combinations, which is good, because I've got four devices. So for each combination, what I would do is have an arrangement of logic gates, so only one of these at a time would ever be switched on. So there'd be a little bit of combinational logic here. So A2 and A3 would be going into there'll be, that's coming down here, this is going across here, and then over here. Okay, this little block here is some simple address decoding logic. And what I would want is, for example, if A2 and A3 has the value 0, 0, I want to switch that one on. If A2 and A3 have the value 0, 1, I'll switch that one on. If A2 and A3 have the value 1, 0, I'll switch that one on. And if A2 and A3 have the value 1, 1, I'll switch that one on. That way, what I've been able to do is I'm using devices which are smaller than the size of my memory map for this processor, but I've arranged them in such a way that they each occupy part of the memory map. And I've arranged it in such a way that at any point in time, no two can ever be switched on. That bit of logic in here that I've used to make sure that holds true, that at any point in time, at most, only one of them can be switched on, is address decoding. So that's what this particular topic is about, is what do we put in here to make sure that the things are switched on in the appropriate way. Now, in the case of this one, it's easy. In the case of this one, an AND gate would do, because it would just be A2, whoops, that's not how you write 2, A2 ANDed with A3. Only when both of those are high will that basically switch on. And for all of the combinations feeding into that, that will be low. That's precisely what I want. It's only when that magic combination 1, 1 appears that this is going to wake up. All of the combinations, it will be asleep. And there'll be other logic gates that I could put in there to achieve the same kind of effect. Now, in this case, if you want to know how to do it, let's say we do this one. So that's a 0 and a 1. What I could do there is I could put an inverter here, and then this one coming in here, and then my AND gate again. So now, when this goes low and this goes high, low becomes a high and a high, goes high, switches this on, for example. So, address decoding in itself generally doesn't require too much in the way of complex logic gates, but they have to be carefully chosen. Now, if I was to draw the memory map of this device, so this RAM, I have 16 locations going from 0, 0, 0, 0, this is all in binary, to 1, 1, 1, 1. okay, and the RAM occupies the whole thing. So that location there, XX, would be that location down there. This location up here, YY, would be that location up there, YY. If I was to draw the memory map of this system, it would look slightly different. Let's say we'll call this R1, R2, R3, R4. What you would find is from location 000 to, where are we going to go?
011.
Yeah. You don't have to draw this.
Can I be already?
Now you know why I only did 16-bit memory. I mean, 16 locations. That's all the different locations. So for those 4 locations, remember this is the A3, this is A2, this is A1, and this is A0. If you look in this region, both A2 and A3 are low the whole time. Well, that would correspond to when R1's awake. So those 4 locations would be locations where only R1 is awake. The next one here would only be where R2's awake. Here when only R3's awake, and here only R4's awake. The A0 and the A1 will actually be used to tell me which of the 4 memory locations within inside R1, R2, R3, R4 I'm actually talking to at a particular point in time. You are expected, and we'll do a little bit, a few slides now, but next week we'll be picking this up again on Thursday, remember. It's quite a common exam question to be told, oh, you've got a processor with a certain amount of address lines, and you bought some chips with a certain number of address lines. You've got to wire them up into a meaningful system so that there's no conflicts, that at any point in time only one of those memories is active. And then to say, for the arrangement that you've come up with, draw the corresponding memory map. Okay? So this kind of thing I'm doing now is very cool. I'll push it down. I'm going to put some slides up in a minute. I won't put that just yet. So address decoding, the purpose is to ensure that if you've got multiple physical devices connected to the address lines, for any particular combination of those address lines, at most only one of those devices is awake and able to be accessed. And we do that by using combinational logic, which is attached to some of those address lines. And that combinational logic is normally connected through to a chip enable on the external devices. So here's an example again. So in this particular case, we have a processor that has 16 address lines. So in theory, it can address up to 64K, or 65,000, however many different locations. And we've bought 2 devices which are 1K byte each. Now, we're being told, well, let's wire it up in different ways and let's see what happens with the corresponding memory map. So each of those devices has 1,000 locations within it. That tells you that each of those devices is going to come with 10 address lines. Because 2 to the power of 10, I think, is about 1,024. So when you buy this 1K RAM, it will have 10 address lines on it. It won't have more than 10 address lines because there are actually only 1,000 locations within it. So it'll have 10 address lines and there'll be a chip enable on it. And that's about it. Now we've got to, with our 16 address lines, we've got to use 10 of them to talk to the 10 address lines on that device. And then from the remaining ones, we're going to do some address decoding that's going to feed into the chip enable to determine when one of those should be awake and when the other one should be awake. Now, the way that we do this, there are different ways of doing it. Life is never that simple, and there are lots of choices in life, and there's even choices when it comes to address decoding. And in terms of address decoding, there are three main types of address decoding. What's called partial address decoding, full address decoding, and block address decoding. And I'm going to show you each of those in turn. So in the case of partial address decoding, although I have 16 address lines to connect up to switch on and off those two 1K memories, I'm not going to use all 16 lines. Some of them I'm going to ignore. So here's an example of partial address decoding. Now, of the 16 lines that I have, 10 of them are being connected to the 10 address lines that are provided by the device itself to talk to the 1,000 different locations within it. The device also has one chip enable, and you can see this one chip enable line, in one case I've connected it to A15 directly, and the other case I've connected it to A15 through an inverter. No matter what you do, it's impossible to have these two devices switched on at the same time. Because whatever's happening on A15, one of them will be awake and the other one will be asleep. If we were to draw the memory map for this, it would look like this. Each of these little strips corresponds to 1,000 little memory locations within the device. What you see here is when A15 is low, the values A0 to A10 allow you to talk to one block, the memory. The same happens again. Now what's happened here is A11, A12 has got different values, but we didn't wire that up. So irrespective of the state of A11, A12, A13, A14, provided only the A0 to A10 are what are wired up here, and the A15 is low, we'll still be able to wake up one of those devices and talk to the memory locations within it. What we have here is what we call aliases. We have multiple combinations of addresses that would actually wake up the device and allow us to access it. What you don't see, there's no locations here where both it's blue and green. So although there are aliases, there are multiple combinations of addresses that wake up the device. There's no combination that exists that wake up both devices at the same time. So it's safe, it's okay. Okay? So, effectively what's happening, when A15 is low, this device is switched on. And then for all combinations of A0 through to A9, we're talking to different memory locations within this device. Now, there are lots of different combinations of A10, A11, A12, A13. Well, they're not wired up to this device. So for all those different combinations, this device will still be awake. All that matters is A15 is low. That's why we're getting all these aliases. You'll notice the complexity of the address decoding is phenomenal. It's just one inverter. So the advantage of partial address decoding is the complexity of the address decoding is very, very simple. The downside of partial address decoding is there'll be multiple combinations that exist in your memory map that effectively allow you to access the same device, which is wasteful. Let's just have a quick look at the other extreme. Have I got the other extreme here? Yeah. This is an example of full address decoding. You'll notice A0 to A9 is wired up just the same as it was before for accessing the internal memory locations within each device. What's different is what we do with the rest of the address lines. In this case, all of the remaining address lines are being used feeding into address decoding logic. There is only one combination here that would make that NAND gate go low. That's when all of these lines are high. all of the combinations of those lines, this will be asleep because this pin will be high. So it's unique. Just one combination of values, A10 to A15, will actually make this switch on. The same is true here. We've got our NAND gate and an inverter feeding one of them. There is only one possible combination of address lines A10 to A15 that will switch this device on. Yeah?
What do you mean when you say it's wasteful in the other example?
It's wasteful because in the previous case, the whole memory map is occupied by those two memories. There's no spare memory left over for other things.
But the ones that aren't connected, you could use that for something else, couldn't you? Because they're not used for anything.
Now you've got to be careful. If you use them for something else, that's something else, and that's active at the same time as those memories are active, you have a problem. So you can use those for something else, provided you do additional decoding to make sure the two memories are switched off.
Yeah, but you can still use those empty ones as the decoding lines and stuff.
You could use those address lines for other purposes, to control LEDs and things like that.
Like, I would have thought this one is wasteful because you don't need to use all the lines. You couldn't.
It's true.
The other one, the problem is, one way or another, one of those two RAMs is always going to be on. Okay? Now, if those RAMs are connected to your data bus, that data bus is always in use. It's either in use connected to RAM 1 or it's in use connected to RAM 2. So you can't use your data bus for anything else. Because if you try and connect it up to something else as well, you've got a conflict.
But the RAM is still on.
If you look at...
but you could just write on the empty ones and leave in either side of it the same.
I think what he's trying to say is, can you not use combinational logic with the other ones too?
Yes, you can, absolutely, yes. And I'll show, there are compromises. But as it stands, if those other address lines you want to use them for other purposes, and it's got nothing to do, you're not using them as part of an address bus, they're just using as kind of lines to fiddle with, you can do that. But the point is, if we go back to that full address decoding, I haven't really shown it. Let's go back to the partial decode. In this particular case, what's not shown here is these RAMs are connected to a data bus. Okay? And when A15 is low, this RAM is always switched on. Which means that effectively the data bus is always in use by this RAM. When A15 goes high, this goes to sleep, so the data bus is not in use by that, but under those conditions, this is using the data bus.
But you could still write to A10 and A14 and just...
You could write, yes, you could write to those and use them for other purposes, that's true. Yes, you can do that if you want to.
So that's why I would have assumed the other way is wasteful, because you can't use them for anything.
And if you were doing port mapped I/O, that may be a reason to do that kind of thing. So I'm not saying what you're doing is wrong, it's possible, but this is considered by some people to be wasteful in terms of, if we look at the memory map, all the different combinations of values on the address bus, for all those different combinations, if you like, for many of those combinations, one of the RAMs is active, and for all the others, the other RAM is active. Now, you might say, well, who cares? Well, that's fine, unless you want to have some of this memory map associated with a third device or something. And you can't do that as it stands with that architecture. You would have to introduce additional address decoding, which is possible. Let's move on a minute. We can always talk about this afterwards anyway. So, full address decoding. Well, I've gone the wrong way now. Silly me. That is. So, full address, no, that's not full address decoding. Find it eventually. There it is. In full address decoding, the complexity of the address decoding logic has increased. Now I need a 6-input NAND gate here, and in this case a 6-input NAND gate and an inverter. So it doesn't sound like it's increased by much, but you go and try and buy a 6-input NAND gate, they don't normally exist. So you would have to achieve that with multiple layers of logic or something. So the complexity has increased. But if I draw the memory map for this, it'll look like that. So now in terms of the memory map, there is only one combination of those high-order address lines that wake up one of the devices. And there's only one other combination that wakes up the other one. And all the other address combinations don't wake up either of them, and so they could be connected to further devices without causing a conflict. Now, that's not to say that that's any better or any worse than the other one, and if you like the other way of doing it, you can do it that way. But we're looking at the trade-offs between partial address decoding and what the impact is on the memory map and full address decoding. In full address decoding, there are no aliases at all, because there's no multiple combinations that can wake up the same device. There is only one combination of address lines that can wake it up. In partial address decoding, there are multiple combinations. Now, you can actually have a special type of partial address decoding, which we refer to as block address decoding, where it's kind of a compromise between the full address decoding and the partial address decoding I showed you before, which was the kind of minimalist approach. So in this particular case, I've still got my 10 address lines here, which are for identifying internal locations within RAM 1 and RAM 2. And some, but not all of the additional address lines are being fed into the address decoding circuitry. In this particular case, the advantage is that instead of having a 6-input NAND gate, I only need a 3-input NAND gate, here and here, which I can buy. So it's a bit cheaper. If we look at what happens with the memory map with this combination, you'll see that we get aliases, but we don't get aliases throughout the whole of the memory map. We only get it confined to a specific region. Now you might say, well, who cares? It means that I can connect additional devices, and provided they sit elsewhere in this memory map, that's fine, it's not a problem. What I have to do is to make them sit a particular place in the memory map, I have to provide the appropriate address decoding so that they'll be awake when addresses within that range are activated. So there's full address decoding where there are no aliases, but you need the most complex address decoding logic. There's the kind of minimalist partial address decoding where you do the absolute minimum to make sure there's no ambiguity, there's no two devices switched on at the same time. That uses very little address decoding logic. And then there's this kind of compromise where we use a slightly more complex address decoding, but we don't go as far as full address decoding, which means that we do get aliases, but not as many as you would get with the minimalist partial address decoding. So let's just have a quick look. We're going to leave it there, and then next week on Thursday we're going to look at doing address decoding for a horrendous circuit. Okay, it's kind of your worst nightmare address decoding. We'll go through that one, and then we'll look at other ways of doing address decoding too. So it won't take us that long. So anyway, have a good weekend, and I'll see you on Thursday.